finish the old one. We're a bit behind, but don't worry. Just do a bit less revision.
Revision.
No. Revision is boring and more of it's funky.
It's boring but necessary.
That's not. Okay, so this was the homework. Anybody has? Does anybody have the solution? No. Mary, you have the solution? You want to tell us? No. Why not? Do you have both questions or just one? Both? So how does the graph go? Coloring. Okay, shall I say it then? But no, you have to learn to. In fact, there should be what there should be is there shouldn't be any tests for coursework normally. What should be is in tutorials you should present the solution of homework problems and then you get marks for that. Should be the something. Okay. Anyway, so problem one. I won't write the algorithm very precisely, but the basic idea is that you can start anywhere. And you start in any vertex. And use one of the colors that you have. So you only have two colors. You want to color the graph with two colors so that vertices that are neighboring wouldn't get the same color. Okay? So you can color any vertex that you start with green. Did you do that? Yeah. Next. I don't think Mary's volunteering any information. Okay, so next, obviously, when you look at all the neighbors of this vertex, you don't know how many there are, but all of them have to get the other color. Okay. Now red. So far, so good. Okay, now, the problem is that you have some neighbors there. In the third level, they all have to be green. And in the next layer, maybe some of them don't have any more neighbors. In the next layer, they all have to be red. And so it can continue, but what can go wrong? What could possibly go wrong? If anything. Well, I don't think we should pretend that any graph can be colored with two colors. So there must be something that could go wrong, right? Did you get anything that could go wrong? You don't want to tell us. Okay, so for example, when you have a graph that is just a triangle, you've got this graph. Well, it's in K because I'm thinking ahead. It's got K3. Not be two colored. Screen, so make it a bit small. Okay, because well, it cannot. So you start with green, and then all the neighbors have to be red. Well, but this guy can't be red, or it can't be green. Okay. So one thing that could go wrong is that somewhere here there's going to be an edge. Or another thing that could go wrong is that when you have somewhere in the previous layer, and you get an edge between the vertex that's already been colored and one that you have to color in the same. Okay, so the algorithm has to do this, and at the same time, it always has to check that when it's coloring red, because it's a neighbor of a green layer, that nothing is going back or sideways. That would spoil the coloring. And then it's doing green again, and then have to check that nothing is going back to a green layer or sideways within the layer. That would spoil the coloring, and so on. And those are the only two things that can go wrong. So if it never happens that there's an edge going backwards to a vertex in the same colored layer, or that there's an edge going like this within a layer, and you get a proper two coloring. That's an algorithm, and if you analyze it, you can see that it's running in polynomial time because it's not doing so much work really. It's basically looking at every pair of vertices in most ones, really. It's quadratic in the number of vertices, which is polynomial. Okay, so I'm leaving out half of the answer at the end of the actual analysis, but not very hard to do. And we haven't got so much time. Okay. Any questions? Did you get what the problem was, the original problem? Because you weren't here last week.
No.
Oh dear. I should have said it properly. So you have a graph that's given. I didn't draw the whole graph because I was drawing it and as it was progressing. But originally, so when you look at one of them, and then you have to assign two colors. So each vertex gets exactly one of two colors. And if there's an edge, then they must not get the same color. That's the problem. And it's not, and it's the specialty of the number two for the number of colors is that you can do it efficiently. Because if you allow 3 or 4 or more colors, then nobody knows how to do it efficiently. So this approach fails. And here, in some sense, the color is forced because you can't. You know, green, oh, this has to be red, and this has to be red, and this has to be red. There's no choice. Whereas if you allow 3 colors, then you have to choose: is it red or blue? Is it red or blue? Is it red or blue? And you don't know. And so you could do it like this, and you could try red and then go and see it fail. So you go back and try blue, and and so on. But then you start branching too much, and you get an exponential number of runs, kind of, because for every time you have a choice to color the vertex with 2 colors, because it's not forced by anything, then you have to try one, and if it fails, you have to try the other, and kind of grows exponentially the search tree, as it were. Okay? That's the reason why this one is, the two colors is different than the other problems. Okay, question 2 is was to find a CNF formula which is not satisfiable. And what is a CNF formula is if you turn it around like this. It's explained here, but we'll come to that. Let's just get one. So, Mary, do you have one? Because I don't. So now I really need you. Please. X, Y, A, B, C. Do you have it here?
I do have one.
Yeah, let's have a look then. So I don't have one. So you should save me. Or shall I try and create one? Okay, I'll try and create one. So one could be, and it's a very stupid one. So X or Y, and not X or Y, and X or not Y, and not X or not Y. Okay, the shorter one. Maybe we should have taken yours. But we don't want to give it to us, so too bad. Okay, so this one is unsatisfiable, I believe, because whatever X, would you only have one variable? Two? Shorter than this? Would you repeat the same variable in one clause? No. I want to see. No? Okay. No. So, anyway, so can you set X and Y to true or false so that everything will be satisfied? Well, no, because whichever combination of true or false for X or Y you use, there's exactly one of them is going to fail. So that's that probably answers the question. Now we still don't know what it's about, but we'll see in 5 seconds. Any questions? Okay, so okay, so what we did as the last thing a week ago was look at this example and then try to write it as a formula like this, where A was Alice is coming and B was Becky is coming. And I thought it was important. Not I need my notes because I can't remember what to say. Okay, so this sort of formula is called a CNF formula. CNF stands for conjunctive normal form. And that's the next slide. Says everything. I don't have to write anything. So a formula like this. So it's something or something or something and something or something and so on it goes. So that's important. You have to satisfy them all. In each of the clauses, you pick which one you satisfy. That's what makes it hard. Because if you did it the other way around, it would be really easy. Because then you will only have to satisfy one clause, and each clause is easily checked whether you can satisfy it or not. So what's hard is this. Okay, go on. You can read it. Okay, so the computational problem related to this is called SAT, for satisfiability. SAT for satisfiability. It's very easy. The input is a formula in that form that we've just seen. The question is it satisfiable? So can you assign true and false values to the variables so that the whole thing would be satisfied? It's in NP. NP. Did I say what NP was? Well, we said last week what NP was. I hope. No. Non-deterministic polynomial, what it stands for. But what it really is all the problems, decision problems, so yes, no questions, in which if the answer is yes, roughly speaking, then you can easily verify that it's yes. Okay? And easily verify means that if you get some additional information, but not too much, so only polynomially much additional information, then you have a polynomial time algorithm that verifies that it works. So in this case, if the answer is yes, so that means the formula phi is satisfiable. Then, what's the additional information that will do? So what you can get is the true-false assignment values. If I give you a list, which variable gets true and which variable gets false, then you can easily check that whether it actually is a satisfying answer. Let's go through each clause. Oh, this one says it's true, this one says it's false, this one says it's true. So I get it true. The next one, oh, it says this. Okay. Like this, you go through. And it's easy to check. And it's quick time to check. But a given assignment that will be mathematical notion of it. I should say makes the formula. Okay. So if someone gave me a formula like this, I was claiming, and someone claims X being true and Y being false, for example. Well, then it's easy to check, right? Because X or Y true, okay, good. Non-X, Y, false or false, so that's false. No, you're cheating. And that's basically the checking algorithm. Okay. Any questions? That's okay. Now, what comes is not easy. This is where it starts being. Okay. This is where it starts being hard. I'm doing everything too slowly. Spend time explaining. Okay. So, polynomial time reduction is an algorithm. Function yes, but it's completely in polynomial time, so it's a function together with that algorithm that can. What it does is, for example, explaining the definition. Just think of an example. So we saw, for example, how one can solve the batch planning problem in certain cases using the shortest path algorithm. Okay? So we can say that A is the batch planning problem. And B is the shortest path problem. So what this algorithm does, it takes an input that is an input for the first problem, and then it computes something, and it spits out the problem for the shortest path problem. Okay? And then that's it. That's all it does. That's all the reduction. And in order for it to be a reduction, it has to take. Okay, so what we're looking at is the decision version. So there's a version where you don't want to know the shortest path, but you're only asking whether the shortest path is at most a number. And you don't want the batch planning problem. You're not really interested in how much it's going to cost. But in addition, you take some number and you're asking if there are a way to plan production in such a way that the cost would be at most bits. So they're both the decision versions of these problems. And what we want is that for it to be a real reduction, it should. The answer was yes on some question, on some input, then we want the answer to be yes, and the input that it spits out. Otherwise, it would make sense. Otherwise, we would lose the input. So we want, if I get a batch planning problem and some cost, we want sort of path problems or a graph and some length of path. And the answer was yes, can do it with this cost. I want yes, the shortest path is at most this. If the answer was no, you can't do it, possibly do it with at most this cost, then the answer should be no, you can't possibly get the path. Do it. And to preserve it. So we saw a reduction when discussing how to solve batch planning using shortest paths. And another thing we saw was we could solve the knapsack problem using shortest paths. And I say it wasn't a polynomial time algorithm because the graph that came out of it was too large, and it grew exponentially. And so that was an example where you get a reduction. For any instance of the knapsack problem, it will give you an instance of the shortest path problem. Again, you could do a yes to yes, but you couldn't do it in polynomial time because the thing can't create a thing which is exponential in size in polynomial time. It's not possible. Just to write it down, you need exponential time. If it was easy, write it down and writing it. That but this polynomial time reduction is kind of key to so there's an important thing missing here, which is that maybe it's a theorem, but maybe it's just an observation, so I'll just write it as an observation. So if you have a polynomial time reduction from A to B, and B has a polynomial time algorithm, you think of polynomial time as efficient, then what happens? You have a problem, some problem like, sorry? That's exactly that. And also A, then A also has that. Because you could do the algorithm, you get an input for A, and you use your polynomial time reduction to create an input for B. Then you use the polynomial time algorithm to solve B. And the running time you get is just the sum of two polynomials. So it's polynomial to polynomial. So everything is efficient, and you can solve A. So that's again thinking of that one example that I gave is if you know how to solve shortest paths, then basically any problem that, like the backslamming problem, you can also solve it. Well, maybe you can solve it in polynomial time in a better way than using this reduction. Perhaps, but you can definitely solve it in polynomial. This is not saying that that's the best way of doing it. There is a way of doing it. Now, if you revert it, so if you look at the converse of this statement, if A can be reduced to B and A has no polynomial time algorithm, then B. So, no? So there's nothing really very deep about it. Okay, so this somehow tells us that this reduction kind of means that B is harder than A. B is at least as hard as A. B is easy, then A is also easy, and A is hard, and B is even harder. Definitely not easy. And that's not right, sorry. That motivates the definition that the problem is called NP hard if any problem in the class NP has a reduction to it. Okay, so these are the hardest problems. There's nothing that, everything that is in NP is already either as hard as my problem being or easy. Kind of definition motivated myself. And now there is a bit of a formal distinction between an NP problem and the fact that there might be even harder problems than NP. Let's not go into that. So, the picture kind of looks like this. We've got, so if this is the class NP of all the non-deterministic problems, so they're all for the yes answer, you have a good among them, there are the polynomial time solvable ones. Because if there's a polynomial time algorithm for a problem, then that algorithm by itself already can be used to check the yes answer. So it was good as and somewhere at the top, those are the NP complete problems. So these are the hardest. The hardest problems in NP. And if you could solve any of them, you could solve everything. If anybody found an efficient algorithm, or an algorithm for any, and But nobody knows. So present is the current state of science is that nobody knows whether this whole plot is solvable in polynomial time or not. This is where we stand. People have been trying for the past 50 years or so. So, yeah, that's good. So what are the practical? This is what I've just said. If an NP-complete problem found any one of them, we found a polynomial algorithm for it, that would mean that every problem in it that P is the path of polynomial time problem. And no one, and because no one knows polynomial time algorithms for the hard problems, what people do in practice is when they encounter an NP-complete problem, they need to solve it. Like, for example, the knapsack problem in syntax application. Well, let me tell you what. If they encounter in practice some NP-complete problem, they need to work around. Because the algorithms that are known for NP-complete problems are just practically not very good. And if you get a problem of any kind of realistic size, you can't do so. So there are some without doing something. Okay? So one thing that you could do is you try some heuristics. So you just try do something, and you have no guarantee. To get the right answer, the optimal solution. And another thing you could try is, what people do is approximation algorithms, where at least you get an approximation algorithm which does run in polynomial time, but maybe it doesn't give you the best, the optimal solution. So maybe, remember we were talking about traveling salesman problem, ride out and visit customers. It's like a planned delivery, and you want to spend the least distance traveling. So maybe you can say, okay, well, I don't mind if I don't get the shortest possible one, but perhaps it should be within a factor of 2 of the optimum, so not worse than double the optimum. There are algorithms that work under some conditions and distances. There are some like this. You shouldn't expect, if you get an NP-complete problem, you shouldn't expect to solve it exactly and quickly for large instances, large size of inputs, large real-life problems. For example, I'm killing my time because giving examples, but yeah. So what are the NP-complete problems? And there's a long list in a book, but we are just going to. When we finish today. So we're going to finish it next week, which we're going to link with revision. There's a question on this in the exam. And so we'll have a look at the questions from last year and and the exam question. But I do want to say the first thing is that okay, so it's proof that the satisfiability problem, you get a CNF formula, and the question is it satisfiable or not? That is empty. Tell it was an MP, but it's a number. And the question is, how do you prove that some problem is NP complete? So when I go back to the definition is kind of tough. And so you have to prove that for any other problem which is in NP, and you find a polynomial time reduction, and that's a whole lot of problems. So it's kind of how would you go about it? I mean, this doesn't look very nice as a proof. Look at all the possible problems in NP, which there are lots and lots. But luckily, the thing is that if you have one complete problem, then everything gets much easier because get an complete problem, you can reduce that complete problem to something else, and that something else is also NP. And the proof relies on something that I get. But the question is, so what does it mean for D is NP hard means any A in NP can be reduced. So any A can be reduced to B. Now we want D is NP hard. But what does that mean? Any A in NP can be reduced to C. But the idea is to use kind of go in a roundabout fashion through B. But if A is any, we know number one that A has a reduction to B because we know that B is NPR. And we know number two, we know that B can be reduced to C because that's what we're assuming. And if we do the second reduction after the first, then we still get a polynomial time algorithm. And it reduces A to C. This is the idea of how you can now prove many problems that are NPs that are hard to solve. Unless we've all been stupid and not found the obvious polynomial time algorithm for all but again, the idea is you already have some to start with. For example, proof gave you SAT. So now you can start reducing SAT to various different problems by graph takeover. And then whatever you manage to reduce it to in the point loss of it. If somebody, for us, there's many problems with a long catalog. There was already a very long catalog of NP problems. Anybody found colonial time algorithm for any of those problems, then that would solve everything collapse and all this what is NPR and what is not. That would all be useless because everything would be solved. But nobody has. Generally believe, even though there's no mathematical proof, generally believe that can't solve them. Any questions? The only thing that remains is, I think, is the last slide, and there it is, which proves that. On the handout. It's still on the handout.
Yeah.
Good.
There's one more after it.
Yeah, which is that integer programming. That's the end. Also, we look at why integer programming is not. Is that part of the question from last year? It's still part of the question. All right.
Solve the optimal. Let's say I would obviously.
But you have to grow it. And you can't take the easy 3 by 3 by 3.
Like that, like 27 times.
Possibly, but that's a finite number.
But it's solving it in optimal time. That's one of the end of that.
That can't be 3 by 3 by 3. Because there is a quick algorithm.
There is a quick algorithm.
Yes. But nobody knows it, perhaps because there isn't. So, yeah. But the thing is, and now it's actually a question. I mean, it actually is a question. So if you have a problem whose input, there's only finitely many different situations and inputs and you can't do that because what you can do is for each of them, you can just give the answer in a list like a table. The algorithm is just look it up in the table. So maybe nobody knows the table, but can't do that. It's the same with chess. Okay? So if there's a white win or a black win, nobody knows because nobody has searched the whole thing. But it can't be anything hard because there's only many different positions on the chessboard. For each of them, the answer is either black or black. We don't know which one it is, but in theory, but God knows. It's kind of weird, so. Mathematical God knows. Sorry? No, couldn't. Well, I mean, unless there's so if AI can solve it, then AI is not not. I mean, AI is a yeah. So AI is yes. Thing is, AI is kind of the model here is kind of different to what AI is trying to solve. Well, it is and it isn't. AI can solve it. It's still, I mean, AI still works in a deterministic fashion. Doesn't do anything else than the algorithm. It changes the algorithm every time because it learns. But it doesn't. The learning is also determined. The whole thing is just an algorithm. There are certain things that are not in this context, like quantum computing. That could be a bit of that could change things, but AI just better able to focus certain things. Okay, good. Any more questions? Yeah, he's a